Right, this is the second lecture on electricity, which is going to focus on resistance. And really, maybe we want to say that this is electricity resistance, and it's part 2. Oh, electricity. So it's a second lecture. So we saw these situations where we create a path and therefore we have current. We have charges flowing from one side of the battery to the other side. And again, it doesn't have to be a battery, but we have a place where there's an excess, there's a place where there's a shortage. We have a path, electrons flow from where there's an excess to where there's a shortage. But what if that was a really good path? What if that path made it really easy for electrons to flow? They were conductors, right? So they were materials that didn't hinder the flow of these electrons. So what would happen then if we had a situation where if we just had conductors connecting the positive to the negative, right? So if this was the case and we turn this switch, we'd actually have a very dangerous situation, right? We would have a situation where there's nothing stopping these electrons from flowing. So there would be this enormous number of electrons leaving one side of the battery, going to the other side of the battery. And all these electrons are carrying kinetic energy, right? So if they have the ability to apply a force to something and make something move. So if we had great paths and we shut the switch right now, all of a sudden we have this enormous number, right? And this incredibly high amount of amps, which would mean there's we're in these numbers of electrons. I don't even know what they are. They're not, they're not gazillions or trillions or quintillions. They're just this huge, huge amount. So this also, by the way, is actually an electrical fire, right? If we create a path and the only thing in that path is conductors, that everything's going to get so hot because of the energy that's being carried in there that things are going to burn up, right? So for example, I'm going to show this and I'm going to kind of show it again. If I create a path, so electrons are coming out this side and going through this side, and we just look at the piece of wire, well, the piece of wire is made up of atoms. And sure, they're not really trying to grab the electrons and hold them. They're willing to let the electrons go by, but there's still going to be electrons going by that are going to push on the electrons that are actually attached to the atoms. They have to push those electrons out of the way sometimes. And also the nucleuses are positively charged, so they have to pull away from those. So even though these reactions are minimized, if we have electron going through, they're still going to interact with the atoms in their path. And if they're going to interact, well, that's going to make these electrons start moving faster. And the faster they move, the more temperature there is, or the greater the temperature goes, because the more kinetic energy there is. So we don't create paths normally that just have conductors. Conductors allow the electrons to get where we want them to go, but they've got a job to do somewhere. So we have other things in the path. And the one thing we're going to talk about in this section is we're going to talk about resistance. So we need to put things in the path to slow down the electrons, right? And that's resistance. Resistance is the measure of the opposition to current flow. It's what slows down the current flow. It's what tries to stop the electrons from moving. This is the one place where unit analysis doesn't really work. Resistance is measured in ohms, and ohms is represented by this Greek letter omega. So resistance is in ohms. We're going to see this is the one place where I don't expect unit analysis, because ohms don't, we could pretend it does and we could figure out what it would be equal to, but ohms isn't naturally designed to equate to kilograms, meters, seconds, and coulombs, where everything else is. So ohms is usually just ohms. And we're going to see some of the calculations we do don't really loan themselves to unit analysis. So when we're dealing with resistance, it's the one place where I don't use unit analysis, because then we're just kind of pretending more than anything else. So resistance is the measure of the opposition to current flow. Resistors are the objects that offer resistance. Resistors are components that convert the kinetic energy of the electrons into heat. So they take away some of the kinetic energy that the electrons have, therefore making them go slower. And they do that by creating heat with that kinetic energy. So unfortunately, we're not doing any labs, but usually when we do these labs for real, at some point someone's like, hey, you didn't tell me these resistors are going to get hot. And they don't burn themselves, but they kind of burn themselves. It's like, well, no, that's the whole point of a resistor. They take the kinetic energy from the electrons and turn it into heat, right? So resistors are not material with free electrons. Free electrons are conductors, right? Resistors tend to be materials that want one more electron in their outer shell, so they try and grab these electrons that are going by, and that's what makes it a resistor. So let's say this material is a resistor. We have these electrons. They're fighting their way through, and as they fight their way through, this area here is what slows down the electrons, right? But understand still, the current flowing out of the battery has to equal the current flowing in, right? Because current is uniform and instantaneous. Now, if I increase the number of electrons that are coming out, now more of them are pushing through there every second, which means these atoms that are attached to the material are going to get pushed more often. They're going to start moving faster and faster and faster, which means there's going to be a higher temperature, right? I make this again so more electrons are coming out. Now we're going to make these move around even faster, right? So some of the kinetic energy is lost, and therefore this material is going to get hotter because of that, or it's going to have an increase in temperature. So that's the way it works. Now, current is still uniform and instantaneous. So if this is a resistor and it slows down current flow, it slows down, If this is a resistor and it slows down current flow, it slows down the current flow going into the resistor. It also slows down the current flow coming out of the resistor because, again, this whole path is getting pushed all the way through. So it's not going to speed it up in some places and slow it down in other places. When a resistor slows it down everywhere because current is uniform and instantaneous. All right, so we have some basic ways that we can look at current flow and look at circuits. One of the most important ones is a series circuit, and it's got a long definition, but you should know it because we're going to talk about it more than once. A series circuit is when the current through the first resistor must equal the current through the second resistor. I'm going to say that differently. When the current flowing through the first resistor must flow through the second resistor. When the current flowing through the first resistor must flow through current flowing through the first resistor must flow through the second resistor, and the current through the second resistor must come from the first resistor. I like that much more. The current flowing through the first resistor must flow through the second resistor, and the current flowing through the second resistor must come from the first resistor. That's what it means to be in series. In my picture here, now we're using schematics because it's easier. I have 3 resistors and 3 resistors in series. All the charges come out, they all flow through R3, but after they're flowing through R3, the only place the electrons can go is through R2, and after they leave R2, the only place that electrons can go is through R1. These 3 resistors are in series. Everything that flows through this must flow through this, everything that flows through this came from this, and again, everything that flows through this must flow through this, everything that flows through this must have came from this, right? So this is what it means to be in series. It sounds like I'm redundant when I compare the first part and the second part, but I'm not, and we'll see as we do examples in the next lecture how we have to make sure we can apply these laws. So we should be able to look at a circuit and we can say, okay, I see the battery, I see the path the electrons are taking, I see the resistors that are in that path that are designed to slow down the electricity, and they're designed to make heat, right? You have plenty of resistors in your home, and the main purpose isn't to slow down the charges, really, it's to create heat. Other times resistors are designed to slow down, right? So they have 2 uses to them, and it depends on which use we really care about, right? The stove, the burners on your stove, well, they're resistors, right? And they're designed to make heat. Right? Inside your hair dryer, there's resistors to make the air hot, right? So there's lots of times we use resistors because we want the heat. Other times we use resistors because we want to slow down the flow, right? Your laptop, right? If you have a laptop like mine, it gets really hot. Why? Because there's a whole bunch of resistors inside the laptop that are controlling the current flow. We don't want them to be hot, but that's just the byproduct of them slowing down current flow, right? So resistors, do both things. Sometimes we only want one of them, but we got to take them both. All right, so looking at this, we have 3 resistors in the path, all slowing down current flow. So if we look at this then, what's the total resistance? Well, if this circuit just had this resistor in it and these 2 didn't exist, there would be 5 kiloohms of resistance. But because I have other resistors in the path, it gets harder for the charge to go through, right? As they go through this one, there's a certain amount of resistance, but then there's more resistance, then there's more resistance. So every time we add a resistor, it gets harder and harder and harder for the charges to flow, right? Imagine that you were in the classroom and you wanted to leave, but there was a person in your way. Well, that would slow you down. And let's say right after that person, there was another person in your way. That would slow you down even more. And then if there was a third person in your way, that would slow you down even more. So as 3 people were in your path, it gets harder and harder and harder, and it just keeps slowing you down. It affects the flow out of the room. So series, we wanted to find the total resistance. First thing we do is we identify a situation as in series. And when in series, the total resistance equals the resistance of the first resistor plus the resistance of the second resistor plus the resistance of the third resistor, and you add them together and they will combine to give us the total resistance. Now, with that said, it doesn't have to be 3, there could just be 2. There could be 20 resistors, right? But in the end, we just keep adding all the resistors in series to get the total resistance. So that's one way that we could look at resistors. We could wire them in series and put them all in the same path. The other thing we could look at, well, if they're not connected in series, the other way that they could be connected is in parallel. And in parallel, it's different. It's actually kind of just the opposite. The current flowing through, the current... I hate when this does this. How do I turn that off? I should know how to turn that off, but I don't know. Alright, so the current flowing through the first resistor cannot flow through the second resistor because they're different paths. So I have these charges, and we're going to talk about this too, these arrows, a little later. We have the negative side of the battery, and I'm going to say charges are coming out the negative side, so I'm going to kind of ignore the arrows in this picture. Well, the charges come this way. When they get to 7, they could go up through R1, or they could go through R2, or they could go R3. But if I follow any one electron out of this battery, they can't go through all of them, right? I follow one electron. When it gets to here, if it takes this path, well, then it's going back to the battery. So the electrons that go through R1 will never see R2 or R3. Again, if a charged electron comes out and it skips R1 and says, oh, I'm going to take this path, that's perfectly fine. But if it takes this path, then it goes back to the battery. It never sees R1 or R3. And the same thing for the last one. If an electron ignores this one and ignores this one and then takes this path, well, then that's fine. The charges that go through R3 will never go through R1 or R2. So that's what it means to be in parallel. We have different paths. So no one charge is going to go through 2 of these resistors. Well, if we think about this, the more paths we create, we have less resistance. We imagine that you're trying to get out of the room and there's all these obstacles in your way. The more obstacles you have to deal with, the slower it gets. But what if you just said, I'm going to ignore all this and I'm going to take a different path out of the room. I'm going to go through a different door. Well, if there was more ways to leave the room, then the room would empty faster, which means the resistance must go down, right? If some people used the front door and there was a lot of obstacles and some people used the back door, well, the room's going to empty even faster. But even if the back door had its own obstacles, it doesn't really matter, right? There's still going to be a faster flow out of the room. If some people went through the lab closet and went out a different room, again, that would be a longer path. But as long as a few people go that way, the room would empty quicker, which means resistance had to go down. So when we connect resistors in parallel and we create more and more paths, we actually have more current flow and we have less resistance. So when we identify a situation as parallel, this is the equation we have. 1 over the total resistance equals 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. We're going to use these equations and examples in the next lecture, but these are the 2 equations. So right now we need to identify a situation as series, or we need to identify a situation as parallel, and then we have to use the appropriate equations, right, which is what this one's about, identifying if we're in series or parallel. The third thing that could happen is that we can have a combination circuit, which means some things are in series and some things are in parallel. In this example, resistors 1 and 2 are in series with each other, but they're not in series with resistor 3. And some people say, well, wait a second, Rob. The electrons that come out of the battery, they go through resistor 3, some of them, but the ones that go through resistor 3 go through 2. So I could say the charges that flow through the first resistor must flow through the second resistor. So hey, that's series. But it's not, because series had 2 parts to it. There was an and, right? the current flowing through the first resistor must flow through the second, and the current flowing through the second must come from the first. So if I look at these two, the current flowing through R3 must go through R2. That's great. But the current through R2, did it have to come from R3? No. Could have came from R4, right? So resistors 2 and 3, not in series because they didn't meet all the conditions. I'm going to turn on my pen again, which means I can't turn it off probably after, but that's all right. Right? If I look at the flow, and let's make it in green, then the current's flowing this way, the current's flowing up, or the current could be flowing this way and up, and then it all recombines and goes through R2. So resistors 3 and 2, not in series because they don't meet the full definition of series. Resistors 4 and 2, again, not in series. Now, resistors 2 and 1, they're in series. Everything that flows through 2 must flow through 1. Everything that flowed through 1 must have come from 2. So I could say these two are in series, but they're not all in series. So this is what I mean by a combination circuit. And I also know the charges that flow through 3 definitely don't flow through 4. One of the electron that takes this path never sees resistor 4. So I can now again say, well, these two are not connected in series. These two are connected in parallel. Now, 99.9% of the circuits out there are some form of combination circuit, right? They're not all series, they're not all parallel, there's some combination, which is really what we need to deal with, right? So here I have some resistors in parallel, I have some resistors in series. What I have is a combination circuit. The next lecture is going to deal with combination circuits, and we're going to put some math to this. How do we determine the total resistance? And once we figure out resistance, we're going to go back to current and apply the current laws to a same circuit. But the next one will involve looking at series and parallel and finding the total resistance based on these equations. Okay. Have a good day.